Hello everybody. This pre-lecture will cover intermolecular forces and how that impacts physical properties. Particularly we're going to focus on boiling point and melting point. Okay? And you'll notice here, if I can get a pen, we're going to focus on attractive intermolecular forces. We could talk about repulsive forces, but we're going to talk about what are the kind of forces that cause something to, say, condense as a liquid or become a solid. Remember, for gases, we assume there are no, and let me say ideal gases, there are no intermolecular attractions. Okay, and that is an assumption for an ideal gas, okay, which is a pretty good assumption. We talked about the conditions of temperature and pressure, high temperature, low pressure, but something even like helium gas. There are weak attractive forces. And we're going to call these, instead of writing out intermolecular every time, we'll call them IM, intermolecular forces. So even in helium gas, there are very weak intermolecular forces, and that's why if we get helium gas cold enough, it will condense to a liquid, and that is at 4.2 Kelvin. Basically 4 degrees above absolute zero. So we have to cool that gas down so low so that the attractive forces can finally take hold and condense helium gas into the liquid state. Okay? But for now, ideal gas has no intermolecular attractions, but certainly to get a liquid or solid, there's something holding the molecules together, and those are what we call intermolecular attractions, IM attractions. All right, this is going to depend, these attractive forces will depend on polarity. We talked about polarity in Chapter 10. So this will be a good practice to review what polarity is, and then if you have a nonpolar molecule, what types of attractive forces are there? If you have a polar molecule, what types of attractive forces are there? Okay, so we're going to break this down into nonpolar, polar, and then also ionic. And there's going to be a particularly strong attractive force in polar compounds that we call hydrogen bonding. Okay, so that's in addition to polar, and we'll talk about when we see that. Okay, so let's just start out. Print this handout out. It is posted. And to be able to figure out polarity, which is what you have to do first before you can figure out what type of intermolecular attraction there is, we have to draw the Lewis structure. And we have drawn the Lewis structure of CO2 before, so make sure you can do that. You also have to do VSEPR. Okay, so this kind of puts all of what we've learned over the last month together. So we draw the Lewis structure, we do VSEPR, we count 1, 2 electron groups for VSEPR. So this will be a linear structure, a linear shape. Okay? Now, here's where the polarity comes in. We talked about this as well. Oxygen is more electronegative than carbon. So the electrons will shift toward oxygen, and we show that with an arrow. Same thing on this side. So these are polar bonds. I wish I had a little more room here, but I copied this in as an image, so I can't expand it. These are polar bonds, but yet you'll notice the dipoles are equal and opposite. So these are going to cancel. All right? And the molecule overall is non-polar. Okay, so we can have polar bonds, and these are certainly polar bonds. Oxygen is the second most electronegative element to fluorine. These are polar bonds, but because of the linear symmetry of the molecule, the bond dipoles are equal and opposite. They cancel out non-polar. Now, the only type of attractive force that exists in non-polar molecules is what we call a London dispersion force. Okay, so that's the answer. What type of intermolecular force? And this type of force exists in all atoms and molecules. but it's the only one in nonpolar. So if you figure out something's nonpolar, what type of attractive force? London dispersion force. Sometimes we just call that a dispersion force, but the full name is London dispersion force. Okay? Now, just to show you very quickly what we mean by a London dispersion force, I'm going to scroll down so I have some room here. Okay? And let's go way down to the bottom of the page. We'll talk about this image in just a minute. So let's take another nonpolar molecule. Okay? Cl2, chlorine gas. Is it nonpolar? Yeah, it has to be, right? Because it's the same atoms bonded together. They're going to share electrons equally. All right? So, we would expect that the electron distribution, or the electron cloud, around that molecule, we'd expect it to be symmetrical. Okay, there would be no charge separation in there. We'd have a perfectly symmetrical electron distribution. But electrons are constantly moving. Okay, the electrons are in constant motion. So at some instant in time, we might actually have something, an electron cloud that looks more like that. So this is some instant in time. Okay, so on the right side of the molecule, there's more electron density. So this side of the molecule has built up a partial negative charge. This side has built up a partial positive. That's a charge separation. This is a dipole. All right. Now, it is not a permanent dipole like we see in polar molecules. This is what we would call, since it happened at some instant in time, we would call this an instantaneous dipole. Okay, nice term, right? Instantaneous dipole. Some instant in time, the electron distribution with electrons constantly moving is distorted to one side of the molecule. We have a temporary dipole, an instantaneous dipole. What that instantaneous dipole will do then is if we have another chlorine molecule next to that, how will the electron density of this chlorine react? Well, it's going to react in the other direction because the electrons are going to be pulled to the positive side. So this will be the negative end. This will be the positive end, right? So electrons are negative. They're going to be attracted to the positive end of the dipole of the other chlorine molecule. And now we have an attractive force between these two chlorine molecules. It's not a bond, but it's an attractive force between these dipoles. Okay? And this second dipole, this was the first one we would call an instantaneous dipole. It just appears at some moment in time. And it forces this one to form a dipole. And we call that an induced dipole. Okay? So it's an instantaneous dipole that induces a dipole in another molecule. That collectively together is what we call a London dispersion force. Okay? So rather than having to say instantaneous dipole, induced dipole force, we just say dispersion force or London dispersion force. Okay? So even in nonpolar molecules, we get these instantaneous dipoles that form attractive forces. And that's why you will see something like chlorine's a gas at room temperature. But look at a periodic table, and you'll find that Br2, which is nonpolar as well, is actually a liquid at room temperature. And then look further down on the periodic table, and I2, which is also nonpolar, is actually a solid at room temperature. So as the molecule gets larger, these dispersion force attractions get bigger. We'll talk more about that in an example up above. But again, the size of the molecule, as the molecule gets larger, these dispersion force attractions get stronger. We'll come back to that. Okay, there's the first one. Next one, So2, Lewis structure. Okay, there's the Lewis structure for SO2. We could draw a second resonance structure as well. But for VSEPR, we don't need to do that. VSEPR, the electron geometry is what? 1, 2, 3 electron groups, counting the double bond just as one electron group. 3 electron groups, trigonal planar. Okay, but what is the molecular geometry or shape? Since we have this lone pair, it will not be trigonal planar. This is where models help. It will be bent. Okay, now the fact that it is bent is certainly going to impact the polarity. In general, keep this in mind, if you add a lone pair, it reduces the symmetry of the molecule, and hence the molecule typically will be polar. Keep that in mind. And so if we draw our structure here in a bent geometry, oxygen is more electronegative. The electrons spend more time around oxygen. It builds up a partial negative. Sulfur will build up a partial positive. You can see that those two bond dipoles, those polar bonds, they are not equal and opposite. They will reinforce each other, and we will get a resultant with the positive end by sulfur. So this would represent the positive end and the negative end between the oxygens. So this is a polar molecule. Okay? So this molecule has a permanent dipole. Okay? So compare that to the nonpolar that we have these instantaneous dipole, induced dipole. Those keep coming and going. They're not permanent. This one is a permanent fixed dipole. One end of the molecule is positive, the other end of the molecule is negative. That's a permanent dipole, and the main type of attractive force is what we call, and you can see why, we're going to call that a dipole-dipole attraction because we have a permanent dipole. So the main attractive force in a polar molecule is dipole-dipole attraction. All right? Now, all molecules have dispersion force. So in this polar molecule, we also have dispersion force attractions. We have both. We have dipole-dipole, dispersion force, but we're going to say this is the main attractive force, particularly for small molecules. And we're going to focus on small molecules. We're not going to go to big molecules. As I said before, as the molecule gets larger and larger, dispersion force attractions get stronger and stronger. So that will come into play for larger molecules. Okay, so here it is. If it's nonpolar, London dispersion force. If it's polar, the main type of attractive force is dipole-dipole. There you go. Permanent dipole, dipole-dipole. Now, last one on the top part of this sheet. Okay, this structure is going to be a little confusing to you. A carbon-hydrogen bond is essentially nonpolar. Okay, you don't really need to know that. When you go to organic, you'll hear that a lot. But what you will notice here is that we have an OH bond. And I thought I changed the color of my pen there. What happened there? Wow, sorry about that. So you will notice that this OH, oxygen is certainly a lot more electronegative than hydrogen. So we're going to get a shift in electron density here. Oxygen partial negative, hydrogen partial positive. This is a dipole. This is a polar molecule. Okay, so this is polar. Now, what we're going to find out, and let me scroll down just to show you this graph. If your molecule contains an OH, an FH, or an NH bond, you're going to have a particularly strong type of dipole-dipole attraction called a hydrogen bond. And I hate the name hydrogen bond because it's not a bond. It's still an IM, intermolecular attraction. Okay, it's between molecules. So, how does one water molecule attract another? Okay, so it's not a covalent bond or an ionic bond. It's an attractive force between molecules. But we call this particularly strong dipole-dipole attraction. This is still a dipole-dipole attraction. We call it a hydrogen bond. Now you'll notice if we don't have hydrogen bonding, these are nonpolar molecules here. Maybe you should convince yourself these are tetrahedral, and they will be nonpolar. We see that boiling point increases with size. So this is increasing size. Okay, and that's what we talked about. As the molecule gets larger, the dispersion force attraction gets stronger, and the boiling point will go up. It'll be harder to break the attraction in the liquid. Okay, we'll talk more about that in the second part of the handout. But we see these anomalies if the molecule has an NH bond, an FH bond, or an OH bond. A particularly strong type of dipole-dipole attraction called hydrogen bonding. So this answer, once we see that this molecule contains an OH, the main type of attractive force is hydrogen bonding. Okay? Now, as always, all molecules have dispersion force attractions, but the main attractive force is hydrogen bonding. All right. Last thing, I don't have an example here yet, but in Ionic, I don't have an Ionic example up above, but if we do have an ionic bond, so if we have something like sodium chloride, Na plus, Cl minus, we call that attraction an ion-ion attraction. What a surprise, right? Attraction between a positive ion and a negative ion, an ion-ion attraction. So that would be, an intermolecular attractive force as well. All right, last part of this handout, down to number 2. Boiling point and melting point. The stronger the attractive force, higher boiling point, higher melting point. Okay, so that makes sense. If we have strong attractive forces in a liquid, we're going to have to heat it up to a higher temperature, a higher boiling point, to break those attractive forces. Same thing for a solid. If we want to melt a solid, if those attractive forces are really strong, we're going to have to heat up that solid even more to break those attractive forces in the solid and get it to melt. Okay. Conversely, the weaker the attractive force, the lower the boiling point, and the lower the melting point. Okay, so how do we compare these? The first thing we have to do is compare things of similar size. And as I've said 2 or 3 times in this recording, the dispersion force attractions will increase with increasing size. So we have to compare things of relatively similar size. Okay? If we compare things of similar size, ion-ion, the ionic attraction, is stronger than hydrogen bonding, which is stronger than dipole-dipole. And I did not leave myself enough room here, I apologize, which is stronger than dispersion force. Okay? So this is strongest to weakest. Ionic attraction, ion-ion, the strongest. Hydrogen bonding is a particularly strong dipole-dipole attraction. So that's stronger than your general dipole-dipole attraction, your general polar molecule. And then if it's nonpolar, just dispersion force, that is the weakest. Again, comparing things of similar size. So again, we have to figure out polarity to predict this. Okay. Now this one's pretty easy. We should recognize NaCl as ionic. Carbon monoxide, you could draw the Lewis structure, but it's a carbon and an oxygen. There's only 2 things bonded together. They're not going to share electrons equally. That's going to be polar. And then nitrogen, 2 nitrogen atoms, the same atoms bonded together, they're going to share electrons equally. That will be nonpolar. Okay? So again, our order is ion-ion. Ionic is the strongest. This is the strongest. Hence, this will have the highest boiling point. So the correct answer to this one is sodium chloride. The nonpolar one, N2, would have the weakest. These would be the weakest. And hence have the lowest boiling point. Okay? So it's kind of a continuation of what we did above. You have to figure out polarity, or whether it's ionic or not, and then rank the strength of the attractions. Okay? Next one, we want the lowest melting point, so we want the weakest IM attractions. So let's look at what we have. H2, two hydrogens bonded together, clearly nonpolar. CO, as we said above, polar. Okay, that's going to be stronger. We're going to cross that one out because once we get to polar, dipole-dipole attraction is stronger. What about CH4? Polar or nonpolar? If we draw the Lewis structure, 4 Vesper pairs, tetrahedral. All 4 bonds are the same, so a high symmetry structure, tetrahedral. All 4 bonds are the same. This is nonpolar. All right, so what do we do with this? We have 2 nonpolar molecules. All those nonpolar molecules have is dispersion force. Which one's weaker? We want the weakest, right? Because we want the lowest melting point. Okay? Which is weaker? And this is where size comes in. Remember, dispersion force increases with increasing size. Okay? So the strength of this dispersion force increases with increasing size. So methane, CH4, is certainly larger than hydrogen, H2. So hydrogen being smaller will have the weakest intermolecular attraction and hence the lowest melting point. So the correct answer is hydrogen. Okay, so a lot to think about. You can see how this kind of puts much of what we've done over the last month together. Sometimes you're going to have to draw Lewis structures. You're going to have to use the Vesper model in a lot of cases. You're going to have to figure out polarity. Is it polar or nonpolar? Does it have a particularly strong type of attractive force where you have an OH, NH, or FH, hydrogen bonding, or is it ionic? Lots of things to think about. Okay, last one on here, and then we are done. Neon and xenon. These are both noble gases. Okay, they are just atoms. Okay, so we assume for an atom that its electron distribution is spherical. If it's just an atom by itself, it's got to be nonpolar. Okay, so both neon and xenon are nonpolar. What type of attractive force will they have? And I just did the same thing again. What type of attractive force will they have? Dispersion force, London dispersion force. All right, so these are both nonpolar, easy to compare. Just like above, we know that the dispersion force attraction increases with increasing size. We want the highest boiling point, so we want the stronger IM attraction. And I apologize, I did not leave myself enough room for this video to write everything I need to write, and it's kind of all messed together. So highest boiling point, we want the strongest intermolecular attraction. Since they're both nonpolar, the strongest one will be the one that's largest in size, because the dispersion force increases with increasing size. Xenon is certainly larger than neon. Look at the periodic table. It's much further down in the periodic table. It goes helium, neon, argon, krypton, xenon. So xenon's way down there. It's much larger than neon. So xenon is larger. It's going to have stronger intermolecular attractions and hence a higher boiling point. Whew. Okay, lots of stuff. You really need to think through this. This really shows if you understood all the previous material. You got to piece together a lot of stuff. Lewis structures, Vesper, polarity. All of this has to come together so you can predict type of intermolecular attraction, dispersion force, dipole-dipole, hydrogen bonding, ion-ion, and predict which will have the higher melting or boiling point based on the strength of that attraction. Lots of stuff to put together. Okay, I will see you guys soon. Take care.